baseball elimination. Over on the radio side of a producer saying, "See that thing in the paper last week about Einstein?" Some reporter asked him to figure out the mathematics of the pennant race. You know, one team wins so many of their remaining games, the other teams win this number or that number. What are the myriad possibilities? Who's got the edge? The hell does he know? Apparently not much. He picked the Dodgers to eliminate the Giants last Friday. Don DeLillo, Underworld. The problem, suppose you are a reporter for the algorithmic supporting news, and the following situation arises late one September. There are four baseball teams trying to finish in first place in the American League Eastern Division. Let's call them New York, Baltimore, Toronto, and Boston. Currently, each team has the following number of wins: New York 92, Baltimore 91, Toronto 91, Boston 90. There are 5 games left in the season. These consist of all possible pairings of the 4 teams above except for New York and Boston. The question is, can Boston finish with at least as many wins as every other team in the division? That is, finish in first place, possibly in a tie. If you think about it, you realize that the answer is no. One argument is the following. Clearly, Boston must win both its remaining games, and New York must lose both its remaining games. But this means that Baltimore and Toronto will both beat New York. So then the winner of the Baltimore-Toronto game will end up with the most wins. Here's an argument that avoids this kind of cases analysis. Boston can finish with at most 92 wins. Cumulatively, the other 3 teams have 274 wins currently, and their 3 games against each other will produce exactly 3 more wins for a final total of 277. But 277 wins over 3 teams means that one of them must have ended with more than 92 wins. So now you might start wondering, 1. Is there an efficient algorithm to determine whether a team has been eliminated from first place? And 2. Whenever a team has been eliminated from first place, is there an averaging argument like this that proves it? In more concrete notation, suppose we have a set S of teams, and for each X in S, its current number of wins is Wx. Also for 2 teams X, Y, and S, they still have to play GXY games against one another. Finally, we are given a specific team Z. We will use maximum flow techniques to achieve the following 2 things. First, we give an efficient algorithm to decide whether Z has been eliminated from first place, or to put it in positive terms, whether it is possible to choose outcomes for all the remaining games in such a way that the team Z ends with at least as many wins as every other team in S. Second, we prove the following clean characterization theorem for baseball elimination, essentially that there is always a short proof when a team has been eliminated. 7.59. Suppose that Team Z has indeed been eliminated. Then there exists a proof of this fact of the following form. Z can finish with at most M wins. There is a set of teams T which is a subset equals to S, so that the summations of Wx summing for all x in T plus the summations of Gxy summing for all xy in T is greater than M times the size of T, and hence one of the teams in T must end with strictly more than M wins. As a second, more complex illustration of how the averaging argument in 7.59 works, consider the following example. Suppose we have the same 4 teams as before, but now the current number of wins is New York 90, Baltimore 88, Toronto 87, Boston 79. The remaining games are as follows. Boston still has 4 games against each of the other 3 teams. Baltimore has one more game against each of New York and Toronto. And finally, New York and Toronto still have 6 games left to play against each other. Clearly, things don't look good for Boston, but is it actually eliminated? The answer is yes, Boston has been eliminated. To see this, first note that Boston can end with at most 91 wins. And now consider the set of teams T equals to the set New York and Toronto. Together, New York and Toronto already have 177 wins. Their 6 remaining games will result in a total of 183, and 183 divided by 2 is greater than 91. This means that one of them must end up with more than 91 wins, and so Boston can't finish in first. Interestingly, in this instance, the set of all 3 teams ahead of Boston cannot constitute a similar proof. All 3 teams taken together have a total of 265 wins, with 8 games left among them. This is a total of 273, and 273 divided by 3 is equals to 91. Not enough by itself to prove that Boston couldn't end up in a multi-way tie for first. So it's crucial for the averaging argument that we choose the set T consisting just of New York and Toronto, and omit Baltimore. Designing and analyzing the algorithm. We begin by constructing a flow network that provides an efficient algorithm for determining whether Z has been eliminated. Then, by examining the minima cut in this network, we will prove 7.59. Clearly, if there is any way for Z to end up in first place, we should have Z win all its remaining games. Let's suppose that this leaves it with M wins. We now want to carefully allocate the wins from all remaining games so that no other team ends with more than M wins. Allocating wins in this way can be solved by a maximum flow computation via the following basic idea. We have a source S from which all wins emanate. The ith win can pass through one of the 2 teams involved in the ith game. We then impose a capacity constraint saying that at most M minus Wx wins can pass through team X. More concretely, we constructed the following flow network G as shown in figure 7.21. First, let S prime equals to S minus the set Z, and let G star equals to the summations of Gxy, summing for all xy in S prime, the total number of games left between all pairs of teams in S prime. We include nodes S and T, a node Vx for each node X in S prime, and a node Uxy for each pair of teams xy in S prime, with a non-zero number of games left to play against each other. We have the following addresses. Addresses S, Uxy wins emanate from S. Addresses Uxy, Vx, and Uxy, Vy. Only X or Y can win again that they play against each other, and addresses Vx, T wins are absorbed at T because it's an ST flow. Let's consider what capacities we want to place on these addresses. We want Gxy wins to flow from S to Uxy at saturation. So we give Suxy a capacity for Gxy. We want to ensure that team X cannot win more than M minus Wx games, so we give the age Vxt a capacity of M minus Wx. Finally, an age of the form Uxy Vy should have at least Gxy units of capacity, so that it has the ability to transport all the wins from Uxy on to Vx. In fact, our analysis will be the cleanest if we give it infinite capacity. We note that the construction still works even if this H is given only Gxy units of capacity, but the proof of 7.59 will become a little more complicated. Now, if there is a flow of value G star, then it is possible for the outcomes of all remaining games to yield a situation where no team has more than M wins, and hence, if Team Z wins all its remaining games, it can still achieve at least a tie for first place. Conversely, if there are outcomes for the remaining games in which Z achieves at least a tie, we can use these outcomes to define a flow of value G star. For example, in figure 7.21, which is based on our second example, the indicated cut shows that the maximum flow has value at most 7, whereas G star is equal to 6 plus 1 plus 1, which is equal to 8. In summary, we have shown 7.60. Team Z has been eliminated if and only if the maximum flow in G has value strictly less than G star. Thus, we can test in polynomial time whether Z has been eliminated. Characterizing when a team has been eliminated, our network flow construction can also be used to prove 7.59. The idea is that the max flow mean cut theorem gives a nice if and only if characterization for the existence of flow, and if we interpret this characterization in terms of our application, we get the comparably nice characterization here. This illustrates a general way in which one can generate characterization theorems for problems that are reducible to network flow. Proof of 7.59. Suppose that Z has been eliminated from first place. Then the maximum ST flow in G has value G prime less than G star. So there is an ST cut AB of capacity G prime, and AB is a minima cut. Let T be the set of teams X for which Vx is in A. We will now prove that T can be used in the averaging argument in 7.59. First, consider the node UXY and suppose one of X or Y is not in T, but UXY is in A. Then the edge UXY Vx would cross from A into B, and hence the cut AB would have infinite capacity. This contradicts the assumption that AB is a minimum cut of a capacity less than G star. So if one of X or Y is not in T, then UXY is in B. On the other hand, suppose both X and Y belong to T, but UXY is in B. Consider the cut A prime B prime that we would obtain by adding UXY to the set A and deleting it from the set B. The capacity of A prime B prime is simply the capacity of AB minus the capacity GXY of the edge S UXY. For this edge S, UXY used to cross from A to B, and now it does not cross from A prime to B prime. But since GXY is greater than 0, this means that A prime B prime has smaller capacity than AB, again contradicting our assumption that AB is a minimum cut. So if both X and Y belong to T, then UXY is in A. Thus, we have established the following conclusion based on the fact that AB is a minimum cut. UXY in A if and only if both X and Y in T. Now we just need to work out the minimum cut capacity C of AB in terms of its constituent H capacities. By the conclusion in the previous paragraph, we know that edges crossing from A to B have one of the following two forms. Edges of the form Vxt, where X is in T, and edges of the form S Uxy, where at least one of X or Y does not belong to T. In other words, the set XY is not a subset of T. Thus we have C of xy is equal to the summations of m minus wx summing for all x in T plus the summations of gxy summing for all pair xy which is not a subset of T, which is equals to m times the size of T minus the summations of wx summing for all x in T plus, if we take out the g star, plus g star minus the summations of gxy summing for all x and y in T. Since we know that C of xy is equals to g prime, which is less than g star, this last inequality implies that m times the size of t minus the summations of wx summing for all x in t minus the summations of gxy summing for all x and y in t is less than 0. And hence, the summations of wx summing for all x in t plus the summations of gxy summing for all xy in t is greater than m times the size of t. For example, applying the argument in the proof of 7.59 to the instance in figure 7.21, we see that the nodes for New York and Toronto are on the source side of the minima cut, and as we saw earlier, these two teams indeed constitute a proof that Boston has been eliminated.